All right, so now we're going to consider a slightly more complicated case where we look at exponential probability distributions, but a submanifold of it. Okay, so so this is estimation, right, in a curved exponential family. Okay, and so what we're going to do now is to consider a submanifold embedded in an exponential family. Okay, and the motivation for studying this is that many statistical model spaces, it's like are described in by this situation. So as before, it's like you consider probability distribution. Okay, so instead of theta as the sort of coordinate, if you will, it's like I'm going to call it u. And then what's going to happen is that theta, which is the coordinates we have in the embedding space, depend, it's like on u. And we just do what we did before. It's like, but then there's this parametric dependence on theta, it's like on u, right? All right, okay. So S, which is the submanifold, it's like in question, is the set of probability distributions of x coordinatized by u, right? It's a submanifold of an exponential family. Right, M, which set of probability distributions which depend on theta, okay, where U is a coordinate system for S, right? So as before, it's like we're going to consider data, observed data, theta. So we have observed data D, all right, and then this specifies an observed point. Eta bar, right, which is x bar, right, which was what we had obtained before. It's like when we're just looking at exponential families without looking at submanifolds, right? So the problem, of course, is that when you construct this observed point, there's no guarantee that that observed point is going to live on this submanifold S, even though you've sampled from this submanifold S, right? So as a simple example of a situation like that, imagine you were in, say, three-dimensional space and you had a sphere, right? And you had data points, it's like, which were all sampled, it's like from the sphere, and you computed the mean of that, right? There's no guarantee that it's like that mean, it's like what's going to live in the sphere. And in fact, if you had sampled all the points and you took the mean of all the points, it would be the center of the coordinate system, right? Which is certainly not on the sphere. So that's just a situation it's like to be mindful of, that because of the fact that this is a submanifold and it's not a subspace, right, then a convex combination of it doesn't necessarily live, it's like on that submanifold, okay? All right, so anyway, so you have this observed data, specifies this mean, right, which is your, estimate, if you will, it's like of the system. And this is going to be, which is in the ambient space, right, M, okay, which but not on S in general. Okay. So what happens then is that now, what you can do is sort of very naturally is that you have an estimate which isn't necessarily, it's like on the submanifold, it's like which you care about. One very natural thing to do obviously is to do some sort of projection of that point, which is an M, it's like onto S, right? So let's see what happens. So yes, okay, so an estimated value of U, right, can be obtained mapping the observed point to S. Okay. Okay. So let's consider a map F, right, from M to S, okay, such that that estimator which you're looking for, U hat, is equal to F of eta bar. Okay. So that's how we're going to construct this estimator. And then so we know the following. Eta bar converges to the true value as n goes to infinity. And we know this because basically what happens is that if you just think of what happens when you repeatedly sample for the same object, it's like, and then you take its average, right? The whole point of taking the mean, it's like, of this is that it reduces the variance in the joint probability distribution, right? So as a consequence of this, as you take more and more data points, it's like the distribution essentially, it's like concentrates, it's like to its true value, right? And as a consequence of that, even though in general this eta bar is not on S, because of the fact that the data is sampled from S, it's like it will eventually, it's like converge to that S, it's like S n goes to infinity. And in fact, it converges to the true value, right? Not just to that. So as a consequence of this, right, what has to happen, if you will, is that the limiting, and I should say this follows from the law of large numbers, right? So any consistent estimator has to satisfy the following property. That we take the limit as n tends to infinity of U hat, right, that has to equal to F of eta of U. All right, so previously we had sort of written theta as a function of U. So the idea is that U is some coordinate system. It's like on this, it's like submanifold S, right? And we can either, it's like write that coordinate, that point, it's like in the theta coordinates or in the eta coordinates. Now I've chosen to write the eta coordinates associated with the point U on the manifold, and I apply F to it, right? And that should be that should agree with the limit of this unbiased estimator. Oh, sorry, consistent estimator. Okay. So let's try to unpack it's like what this tells you. So let us consider the set of points eta in M, which are mapped to U by the estimator. Okay, so this is an inverse image of this estimator F, right? So let's call this set A of U, right? So it's the pre-image, it's like of the point U, it's like under the map F. So it's the set of points eta in M such that F of eta is equal to U. Okay, so this is a codimension sort of M submanifold. I should probably say what the dimension of this is. So this forms a sort of n minus m dimensional submanifold. Passing through eta of U, which is in M. Okay, so the picture to keep in the back of your mind is that you have some submanifold S, which is contained in M, right? And then for every point it's like on S, there is a fiber, if you will, which is the pre-image, it's like of that point. Okay. Okay. So yeah, so the book calls this in sort of ancillary. It's like submanifold is associated with this estimator F. You can think of it as a fiber, if you will, right? So, which is the ancillary submanifold associated with the estimator F. Okay. So this A of U is defined for every U on this submanifold S, and this gives a local, at least a local foliation of M. In the neighborhood of S. This is sort of conceptually like what is called the tubular neighborhood theorem, what basically means that if you have this submanifold S, it's like you can sort of thicken a layer, it's like around it, right? and you can think of, it's like anything it's like in that neighborhood as being locally described by the coordinates on S, where it projects down to, it's like as well as some coordinate in this fiber direction, in this AU direction. Okay. So what we mean by this local foliation is that AU intersect AU prime is empty whenever U is not U prime, and that the union, it's like over U of all these AUs, right, sort of contains this neighborhood U. Let's call that neighborhood U of S. So this is a big U. Okay. All right. So all right. So there's this again this submanifold S, and there's sort of a thickened slice. It's like which I'm calling U about it, and that if you sort of take the union, it's like of all of these fibers, if you will, it's like it will contain it's like that neighborhood of S. Okay, so that's essentially what we're talking about. Okay, so let's see what happens then. So when AU contains eta of U, AU gives a consistent estimator. Okay, so it has to be that if, the eta coordinate associated that it's like has this projection onto S that it stays in that space, right? Right. Okay. So, all right, so you have all these ancillary, it's like submanifolds, which, perhaps maybe it's easier to think of them as fibers, right? So you can take this family of ancillary fibers, if you will. So an estimator defines this family. Let's call that A, which is A of U. And conversely, if you have this limit as n tends to infinity of U hat is equal to F of eta of U, right, then this family A defines consistent estimator. So let me sort of say a little bit about what I mean by this, right? So if you happen to have this kind of local foliation, it's like of a neighborhood of S, right? Then what that's basically saying is that any point it's like which is in this local neighborhood of S, right, has a unique fiber, it's like which goes through that point, right? So that defines for you, it's like exactly this map, it's like which projects down onto S from the neighborhood U, because it's like there's only one fiber which goes through this point in U. And so if you look at that fiber and where it intersects S, that defines for you exactly this map F from U to S, right? So Anyway, so there's this kind of relationship, it's like between this local foliation and this kind of uniqueness of the projection, if you will. Okay, all right. So now the question is, you know, how well does this estimator behave in terms of its approximation power, and to what extent that is related to the geometry, if you will, it's like of this family of fibers. Okay. So the question is as follows. Right. So how does the geometry of A, right, relate to the approximation power, if you will, the performance of the estimator? Okay. All right. So let's see what happens there. So what essentially we're going to do is we're going to introduce a new coordinate that's like along this ancillary submanifold or fiber. And as you might expect, what you want it like for that coordinate is that you want that coordinate to be sort of in the direction which is sort of normal, it's like to this submanifold S, right? So you want to essentially have a coordinate along this fiber direction. Okay. So so let us define a coordinate system. Let's call it V inside each AU, such that you want that V is equal to 0. It's like at okay, such that V equals to 0 at eta U, right, which is the intersection of AU and S. All right, so essentially, again, what you want is a coordinate system. It's like which is, it's like normal. It's like to this submanifold S with the property that that coordinate has value 0 on this submanifold S. Okay, that's again very, very natural. Okay, so now it's like you can coordinatize it's like this neighborhood of S, right? So we denote coordinates of S by U, which is UA, and then A goes from 1 to M. So S has dimension M, right? And then it's, it's like these fibers or ancillary submanifolds, right, have dimension N minus M, okay? And then coordinates on AU by V, right, which is V sort of kappa, and then kappa goes from N plus 1 to N. So together, right, these two things would then give you coordinates for a point that's like in this tubular neighborhood, if you will, it's like of S. So together we get coordinate system tubular neighborhood. Which I called U, right, of S. Okay, so let's call it W. W is equal to UV, right? Or I can write this as W alpha. Alpha goes from 1 to n, and then the first m of those coordinates are coordinates associated with the submanifold S, and the rest of them are associated with these fiber directions. Okay. All right. Okay. So once you have this W, you can of course write these theta. It's like an eta coordinates of this face, right? So we can sort of consider the associated theta and eta coordinates, right? And so I just write this as theta equals the theta of W or theta of U and V, and it should be clear. It's like what I mean by that, right? So there's a point, which is uniquely specified by U and V. It's like, so there's a point in this tubular neighborhood U, which is uniquely specified by little u. It's like a little v, right? And I can write the associated theta coordinates, or I can write the associated eta coordinates, right? Okay, so hopefully that notation is clear. If you prefer, it's like that's sort of one way of saying that I'm writing down a change of coordinates. It's like between these two sets of charts, which I have, it's like chosen. It's like for this exponential family, right? So, right, okay. So if you recall, it's like when we specified this v coordinate system, right? We had the property that when v was equal to 0, it would correspond to a point that's like on the submanifold S. Okay, so so any point in S satisfies the condition that v is equal to 0, right? So S is represented by S is equal to the set of eta uv with the property that v is equal to 0, right? Okay. So now we can look at the Jacobian associated with these change of coordinates. Okay. So the Jacobian matrices of the coordinate transforms between W and theta and W and eta, right, are, let's call that B super I sub alpha is d theta I, d W alpha, and then B alpha I as subscripts is d eta I d W alpha. Okay, and I can decompose them. It's like by breaking up the indices, right? Because I have this alpha index which goes from 1 to n, but if you recall, it's like I also had these indices where I index the u's and the v's separately, so I can break these things up. Okay, and so let's do that. Okay, and these are decomposed into sort of the following components, right? B I A is equal to d theta I d UA, and then B I kappa is equal to D theta I D V kappa, and then B A I is equal to D eta sub I D U A, and then B A, sorry, kappa I is equal to D eta I D V kappa. Okay, so this is in terms of UV coordinates. All right, so anyhow, so with these identifications, we can write down the Fisher information. Okay, so the Fisher information in the W coordinates are given by G alpha beta is equal to B I alpha G I j B j beta. Okay, so all I'm doing here is using the fact that the information metric is a tensor, so I'm just looking at how it transforms under the change of coordinates, right? So that's all I'm really doing here. Okay. And I can decompose it. It's like the same way I've decomposed. It's like the Jacobians, right? I can essentially now partition up. It's like this metric into the parts associated with the U coordinates, or part associated with V coordinates, and then sort of the off-diagonal sort of mixed blocks, right? So, and can be decomposed as G is equal to GAB, right? GA lambda, G kappa B, and G kappa lambda. Okay. Then given the data D, right, the U and V coordinates, let's call that U bar, V bar of the observed point. Eta bar, right, is given by eta bar is eta U bar V bar, and then the estimator associated with this family right, A is given by U hat, which is just U bar. Okay. All right. So anyway, so this sort of gives you a sense as to how do you extend. It's like what we had done before. You know, from just considering it's like the entire exponential family to a submanifold of the exponential family, right? And then, yep. So the next thing it's like we're going to do is to sort of discuss, well, you know, it's like how, in some sense, it's like the curvature, it's like of this submanifold, it's like embedded, it's like into the ambient space of exponential families, it's like affects the quality of this estimator, right? So intuitively, if you think of having something like a projection, right, then the quality of the projection depends in large part on the question of whether or not this submanifold is somehow nice and flat, right? And you could imagine that the more curved that submanifold is, it's like the poorer the quality. It's like of the estimator. It's like when you try to project onto it. Okay, and so we'll discuss that more carefully. It's like in the next section. So let me just stop here for now.